Before we start our journey to learn more about advanced rack, let's see some components of the simple rack. Here I created two different flowcharts, one regarding simple rack and one regarding advanced rack. So let's understand what is the pipeline in simple rack is like. So I have already made a video, a detailed video in fact, on how to implement the simple rack. And the goal of this rack pipeline is to use the text in Bhagavad Gita. It is one of the Hindu scriptures. We'll use all the documents that is in the Bhagavad Gita as our document base. And whenever a user asks a query, we're going to look it up in the context of this Gita and answer to the user's question. So that was all our rack pipeline. And this is how we built it last. First, we got a PDF of the Bhagavad Gita. Then we extracted chunk. First, we read the PDF using something called PyPDF library. And then we extracted the entire text from the PDF file in terms of text in a large text file. And then we divided that text file into several chunks. In this case, we use a very simple token based chunks that we say that, okay, let's say we want 50 tokens in one chunk. Then after 50 tokens are exhausted, then it goes to the next part of the document and then it extracts 50 more chunks. It does so on and so forth and creates divides our entire database into several chunks. Following that, what we do is we import a sentence encoder. That means chunk is basically kind of like a paragraph, you can say. So our goal is to encode this paragraph into numbers or vector embeddings. For that, we are going to use this SentenceTransformer library from SentenceTransformer library, and I am using this all MiniLM model. And what again, using this particular model, I converted all of my chunks into a vector representation, and I saved that in a vector database. This is basically what is a vector database. There are many ways you can use a vector database. For me, I just use a PyTorch tensor. But when you have like millions of documents, you would like to use, let's say, Postgres, SQL, or there are like say ChromaDB. There are many such vector database that you would like to use when you have a large database. And after this is the first stage of the rack where this is the document pre-processing. So for example, let's say this is the user's query, that what happens after that. If we do not use any rack system, then most probably the LLM is going to answer something. It's not going to answer nothing, but we cannot say that it will belong to the Bhagavad Gita. Or also we can prompt engineer a little bit to say that, okay, give it based on Bhagavad Gita. So in that case, what happens when our language model is a large language model, like let's say the 4.0 mini or something like that, then it's okay. It can learn and can give you very good answer with citations. But what happens when we use, let's say, a very small language model, let's say like just 1 billion parameter model, there are like LLaMA models, then it doesn't do as good as a job. It probably hallucinates. It doesn't stick to what question you ask and many other problems. So to avoid that particular hallucination, we are going to create this RAG pipeline. And I'm going to run this on my system. I'm not going to use any API. And I'm going to use the LLaMA 3.2 billion parameter model in a quantized format. So it takes less than 2.5 GB of GPU RAM. So if you have just a consumer GPU, let's say even with 4 GB, it will work fine. It is a good way to play around with the LLM model before you start paying for APIs or something like that. So yeah, back to the topic. So what happens after life? So this is our question, and how we compare this. So now our goal is to extract relevant chunks from our database, which are very similar, which are maybe useful to this particular question. And for that, what we can do is we can compare the embeddings. We already have the embeddings for all of the chunks we have, and we can generate an embedding for this particular query as well. And then we do a similarity search. We do a similarity search in our vector database. And from that, we retrieve, let's say, top 5 or top 10 similar embeddings. And as we have the embeddings, we can get the corresponding chunks or the text as well. So these are basically text and these are basically the vector embedding. Let's say we got chunk 11, 267, 73, 64, and 30. These are the chunk number that we retrieved, which according to our model, according to our RAG pipeline, is similar to our question. Then it's very simple. Then we pass the user's question along with the context. Context is nothing but just a concatenation of all the chunks that we have retrieved, and we pass it to a LLM. In this case, in our case, it was a LLaMA 3.2 billion parameter model. But this thing is not optimal, and we can definitely do a lot of improvement here. In this video, I'm going to show you how you can improve it. So let's go ahead. So let's see how things change in the advanced track. First big change we see here is I'm not using the PyPDF to extract from this PDF file the text. Rather, I'm using small Docling. So the Duckling is a free open source project which can do many document extraction, especially for let's say RAG pipelines. It is also integrated into LangChain if you are comfortable using LangChain. So yeah, this is as simple as this. You import the document converter and you pass your, let's say, your PDF file path into it, and it converts your result. It can give you a result rather in, if you want in markdown format, if you want in text format. If you have a lot of equations in your data set, it's also good at extracting that as well, table or as well. So instead of extracting just pure PyPDF method, because then when we were using just PyPDF, it was not understanding whenever there is a line change, it was just separating words based on that. But here it's not the case. It gives us a very coherent piece of text when we extract. So this is an improvement. This is an, let's say, advancement in our chunking method, that our chunk will have more semantic text in that. There is no word break. So if our chunk is more semantic, that means our embedding will also be more representative, because it totally depends upon how your chunks are created in creating this embedding. So basically, just using small Duckling can improve this entire pipeline. Now let's see in the second stage. In the second stage, what we're doing is we got a question and we are looking for, we were directly converting this query into an embedding and then searching for similar chunks in our database. But this might not be the ideal method. What we would like to do is query rewriting. That means we would like to enhance this query to better match the context of my document. For example, this is my code for query rewriting. What I created is a conversation, which I will pass later into the model.generate, and it will generate me advanced query. And this is my basically the text prompt. Your task is to take the user's natural language question and rewrite in a way to make it easier to retrieve the most relevant things from Bhagavad Gita. The rewritten query should preserve the original meaning but include spiritual keyword, because these spiritual keyword are more time occurring inside the Gita, such as dharma, karma, atma, these things, meditation. The output should be single, concise, clear query that capture the essence of the user's question using language aligned. And then I also gave like some example that you should it should refer to. So after that, let's say this was my query. Is there an afterlife? What happens when we die? And this is the rewritten query. Teaching on the nature of soul's post-mortem existence, like the concept of karma, rebirth, ultimate reality of the self. So yeah, it rewritten this query so that what we can do is we can better match with the chunks in our chunks that we already retrieved from this database. This just rewriting the query can enhance this entire pipeline. And there is another part. There is another stage in the document retrieval we are doing, what is called re-ranking. So in the similarity search, what we are doing is we are taking this embedding and finding the similarity across all the embeddings in our database using something called as a PyEncoder. So this is a PyEncoder where we pass in a sentence A, it gives us a embedding, a vector embedding, and then we find the cosine similarity across other sentences just by passing it. But the problem with this kind of model is it doesn't know, it cannot relate between sentence 1 and sentence 2 inherently. So for that, there is another model called cross-encoder. This cross-encoder model takes both the sentence as input and then gives output in a range of 0 to 1. That means if they are more similar, not even 0 to 1, I think it's a negative some values to positive some values. And if the more positive the value is, that means both sentences are more similar, and the negative or the lesser the value is, they are more dissimilar. But the cross encoder is more expensive to compute because it takes two sentences. So that's why what we do is, rather on retrieving, like let's say top 5, so as bi encoder is cheaper to compute, we can extract, let's say, instead, because before we are extracting just top 5 embedding, now we can retrieve, let's say, top 10 embeddings, and then we just pass this 10 embeddings, we just use this 10 embeddings along with our the query, the question query, not this query but the modified, the rewritten query, to re-rank these chunks again. So for example, what may happen after re-ranking is this, let's say the chunk 267 comes on top, then chunk 73 and the chunk 11 goes to the third. So this is a better and more, it's a better way of re-ranking, because now when we are re-ranking, the model knows about both the sentence. And it can definitely improve our RAG pipeline in having more relevant chunks at the starting of the context. And now it's very simple. We just pass this one into the context to the LLM. So now I'm going to go into the code base and see how they affect the pipeline. So first I'm going to use a question and answer without Duckling, like say without small Duckling, using PyPDF. Then I'll include small Duckling and see how it changes. All these codes are present in my GitHub, and I will put the link to my GitHub in the description of this video. So first, what I'm going to use is I'm going to import the LLaMA 3.2 3 billion instruct model. I'm using auto model for causal from Hugging Face Transformer, and I'm using bits and bytes to do the quantization during inference. You see, it only takes, let's say, 2.04 GB inside my GPU. So even during the inference, it doesn't exceed more than 4 GB. And now let's say I have my PDF of the Bhagavad Gita. Yeah. So this is the PDF of the Bhagavad Gita. It's a pretty long text, having almost 45 pages. All right, and first I'm importing PyPDF library to extract the text. But see, what is the problem here is it gives text in this format. You see, there are a lot of then sectarian. It basically non-sectarian should be in one word. Then it imparts. It should be one word, imparts. So what happens is, when your retrieved text is like this, and when it basically creates a chain reaction of bad RAG pipeline. Now we're going to extract the same PDF but using Docling. So I'm using Docling.document converter, and this is the path to my PDF file, and I'm calling the document converter. Then I'm passing the path to my PDF file, and I'm giving a page range, because up to 5th page there is nothing. It's just like about the author and about the book, and from the 5th page actually the Gita starts. Once we got the result, I'm writing like result.document and then export to text. You can also export to markdown file. There is some you can find it in their documentation, that what are the other methods. It definitely takes a little time, because in the background there is a transformer model which is working to do the processing. But this is a one-time thing. Once you extract text from your let's say document, you don't have to do it again. you can save it directly in your embedding and everything. So now you see, now it did a much better job. For example, see, now it become non-sectarian, which was divided before. Now it's coherent. So now it imparts. So now the words are much better way. They're coherent and everything. Lead to a better RAG method, because all of them, there is also, let's say it gave, okay, this is the subheading and this is the text inside the subheading in a very nice way. Now, next step is the chunking method. Because in the previous video, we are using something called as token text splitter, that we are fixing a fixed size of token, let's say 100. And we are dividing the entire document by, okay, after 100 chunks, go to the next chunk, then 100 chunks, go to the next. So with this method, yeah. So with this method, you see, this is the first chunk, this is the second chunk, but you see there are like things are cropped. The entire sentences are not put together. So here the sentence start and others it cropped. Then there is a full stop here. This is not a very good way of chunking. There can be better. And this is the most, then the next part is recursive text splitter. So in recursive text splitter, it first looks for, the sentence, first paragraph break, then sentence break. It splits the entire text based on that. So, the word doesn't break in between sentences and all. Sometimes it happens, but it's rare. So let's do this. Now you see the sentence are continuing to much longer text. See, now the chunk ended in a proper sentence, in the proper, let's say, question mark. It's timeless book, and you see this another chunk also ended in a proper sentence. Then there is markdown head text splitter also, because this text that we extract from Docling is in a kind of a markdown format. We have the double star and everything, double hash. Yeah, we can use markdown splitter as well. That we say that, okay, split it based on the header, and we get something like this. The chunks are much bigger in this one, but now the chunks have meaning to them, because they are basically a part of they're basically a sub part of the Gita, and they have the entire coherent meaning. So it depends what you want, what type of chunking you want, and all this text splitter are directly imported from LangChain. So for this use case, I'm going to use the markdown text splitter because I found it to be the most efficient. I saved all the extracted chunks in a pickle file so that I can load it whenever I want. And then there is the clean text. 11th chunk, it looks something like this. So now it's time to create the vector database. It's rather simple because we already have our clean text. We'll pass it to the embedding model, and it will convert them to a embedding. So we have total 105 embedding, and each embedding has a 384 dimension. Now the retriever part. So we generate a query. You can choose any query from here, whatever you like. This is just some example I was testing with. And next is the query rewriting. But for now, let's skip the query rewriting. We'll see what is the result with just the user query. So what we do is we use the query, and first we convert it into an embedding, query encoded, and then we find the similarity between the query encoded and all the embeddings that is present in our database. And then we find the top similar embedding and in their indexes. So that's a top 10. So this top k indices represents top 10 similar embeddings to this query. And this is what I'm printing. So see, this is important verses are highlighted. First time readers should. The Supreme Lord said your grip for those who are not worthy of grip. Something related to, I think, afterlife. So there is living for the living, not for the dead. So something like life and death is there. So it gave very high importance to this one, but it may not be. So now let's say chunk 5, chunk 76, chunk 71, chunk 22 is retrieved with this query, the query which we did not do any change. Now let's see what happens when we rewrite the query. I already showed you that this entire function. So now I'll just go ahead and execute it. So now this becomes my rewritten query, teaching on the nature of soul continuation beyond the physical body and the concept of karma's influence on afterlife. Okay, this is the rewritten query, and now I'll use this rewritten query to retrieve several chunk. So let's say if this changes or not, and this is the similarity we got before, by the way. 0.44 was the max. See, now immediately we got a very high similar sentence. And this is a different one. See, chunk 76 is the first. The external individual soul in the body of living being is indeed my integral part. Something like that. So it did change, and which is more coherent in the context of this Gita. And we retrieved, let's say, top 10 chunks of text. And after that, our goal is this one. Already did up to this part. Now is the re-ranking, that we'll use a cross-encoder between our embedding, between our query and the retrieved embedding, and find only the top most embedding after that. So for that, we are going to use a cross-encoder. So I'm importing this cross-encoder. Same is also from SentenceTransformer. And in this way, I just run this code, which will re-rank all the retrieved text by the bi-encoder. So here you see the bi-encoder score was 0.61 and the cross-encoder's score was 009. So basically, whatever the bi-encoder retrieved as the highest similar to the question, the cross-encoder also gave it the same. So it goes like after the retrieved, the chunks becomes the 76 chunk, 93, 38, 40. Let's see if there is any change here. So here it was 76, then there was 9, then there was 93, then there was 22. So this 22 and 9 are omitted, and now this 76, 93, 38, it's like that. So it is, so whatever chunk you get after this are a much better fit. And among them, we don't choose every one, because then there is no point. Then we just should have used the previous one. Now we are just going to use, let's say, top 5 chunk, which are like the most similar to our query. So that's what I did. I find that only the top 5 chunk, the retrieved chunk after the cross encoder, and this becomes my context now. And now it's very similar, very simple, that once we got this, we just pass it to our LLM. So it says, according to Bhagavad Gita, when we die, our individual soul departs from the physical body, but the supreme being or eternal being remains. They continue to exist in the higher realm of existence beyond the physical world. And whatever, it's a very coherent description according to Gita. After that, I put all of them together. So because in the end, this particular application will not generate any value if it's in your Jupyter notebook. It needs to be put in a Python script, which need to be deployed in an AWS server or somewhere. So this is the format what you can use. First, I imported all the necessary things. This is the model. Then I'm importing my vector database that I saved, the vector embedding. Then the sentence transformers. So let's say I pass this question: what is the meaning of life? And the function I created, rewrite query, it immediately rewrites the query. Then I do this is the whole RAG pipeline, by the way. I encode my query into a vector. Then I do a similarity search with all the embeddings. This is my bi-encoder. Up to this point, I retrieve top 10 similar embeddings to that. And then I use my cross-encoder to do the pair-wise similarity. And after the pair-wise similarity, I choose the top 5 similar chunks and put them into my context. See, it's so fast. It didn't even take 1 second to run the entire RAG pipeline. And we got this thing. And now I created this function Gita RAG, where you pass the query and the context, and it gives you the so it generated the text. So yeah, so that was all about this advanced RAG pipeline. I hope you enjoyed. If you have any doubt, don't hesitate to put them in the comment section. Or if you have any suggestion or what I could have improved, that also you can put in the comment. In the upcoming videos, I'm going to show how you can fine tune the llama model with a very simple PyTorch loop without using the trainer, because our goal is not to just train the model but to understand how it is being trained. And along the same lines, I'm also going to make videos on how to train llama model on different languages. So if this kind of topic interests you, do subscribe to the channel, like this video, and stay curious.